To fully understand a group G, you need to take it apart and study the pieces. These pieces are called subgroups. They are smaller groups contained in G. But where do you begin to look for subgroups? How do you find them if there are any? By using objects called cosets, we can create a simple rule that dramatically narrows down the possible list of subgroups. This result is called Lagrange's theorem. Today, we will prove this theorem and show how useful it can be. Quick note, for the rest of this video, we will only be talking about finite groups. A subgroup of a group G is a subset that's also a group. If H is a subgroup of G, we write it like this. Every group has at least two subgroups, itself and the trivial group. The trivial group consists of a single element, the identity element. This is similar to how every positive integer has at least two divisors, itself and 1. But these subgroups are fairly dull. We want to see if G has a subgroup other than these two, something more interesting. The mathematician Joseph Louis Lagrange found a useful test which we now call Lagrange's theorem. He discovered that if H is a subgroup of a finite group G, then the order of H divides the order of G. Recall that the order of a group is a number of elements in the group, and it's denoted by the absolute value symbol. With this notation, we can write Lagrange's theorem more compactly. This is a powerful result. It says that subgroups can't be any old size. There are strong restrictions on the possible subgroups of G. Before proving this theorem, let's see just how useful this is. Imagine you have a group G with 323 elements. You can factor this as 17 times 19. This means the only positive integers dividing 323 are 1, 17, 19, and 323. So any subgroup of G must have order 1, 17, 19, or 323. Earlier, we mentioned that every group has at least two subgroups, itself and the trivial group. The group itself has order 323, and the trivial group has order 1. This means if G has any other subgroups, their orders are 17 or 19. The list of suspects has shortened dramatically. This is a good moment to pause and not get overly excited about Lagrange's theorem. We need to learn its limitations. 17 and 19 divide the order of G. Does Lagrange's theorem say that there are subgroups of these orders? No. Lagrange's theorem is an if-then theorem, which means the converse may not be true. Just because a number divides the order of G, there's no guarantee that a subgroup of this size will exist. In this case, it just so happens that G does have subgroups of orders 17 and 19, but there are groups where this isn't the case. For example, there's a group with 12 elements called A4, the alternating group on 4 elements. The divisors of 12 are 1, 2, 3, 4, 6, and 12, so any subgroup must have one of these orders. However, even though the number 6 divides 12, this group does not have a subgroup of order 6, but it does have subgroups of the other possible orders. This is a cautionary tale on the limitation of Lagrange's theorem. Let's now roll up our sleeves and get to work proving this theorem. Suppose we have a random finite group G with order n. To start, let's check the two easy cases of the trivial group and the group itself. The trivial subgroup has order 1, and 1 divides n. Next, the group itself has order n, and n divides n. So Lagrange's theorem works for both of these cases. Now suppose that G has a proper subgroup H that's not the trivial group. Recall that a proper subgroup is just a subgroup that's smaller than G, one that's a proper subset. We'll represent the group G by a rectangle, and H as a small square inside G. Because H is a group, it contains the identity element. So the identity element for both G and H lies inside the H square. Here's a construction. Pick an element G1 that lies outside of H. Next, let's look at the set G1 times H. This is the set you get when you multiply every element in H by G1 on the left. Remember, we never said that G is abelian, so the order matters. This set is called a left coset because we are multiplying the elements of H by G1 on the left. The key observation is that H and G1H have no element in common. Their intersection is the empty set. Here's why. Let's assume that there is an element in both H and G1H. This means G1 times HI would equal HJ for some elements HI and HJ in the subgroup H. If you multiply this equation on the right by the inverse of HI, then simplify, you get G1 equals HJ times HI inverse. Since H is a subgroup, the right-hand side is in H, so G1 is in H. But this is a contradiction. We specifically chose G1 to not be in H. So our assumption must be wrong, and the two sets do not overlap. We're going to repeat this process until we get to the point there's no element in G that's not in a coset. Pick an element G2 that lies outside both H and G1H. Again, we'll look at the left coset G2H. Using the same argument as before, H and G2H do not overlap. Next, we'll show that G1H and G2H do not overlap either. Assume they do overlap. Then G1HI equals G2HJ for some elements HI and HJ in the subgroup H. If you multiply both on the right by HJ inverse, simplify, you get G1, HI, HJ inverse equals G2. But HI times HJ inverse is an H, call it HK, which means G1HK is in the left coset G1H. This means that G2 is in the coset G1H, but we specifically chose G2 to be outside of G1H. So our assumption was wrong, and they do not overlap. Continue this process until you get to the point that there's no element left that's not in a coset. The result is we have partitioned G into a collection of non-overlapping left cosets. There's one more thing. All the cosets are the same size. There's a short proof for this. Consider a left coset GH. Suppose this set contains a duplicate element. This means GH1 equals GH2 for different elements H1 and H2. But if you multiply on the left by G inverse, you see that H1 equals H2. This means that the size of each left coset is equal to the order of H. If the order of H is D, then each coset contains D elements. We've now managed to split G into non-overlapping left cosets. A word of caution, H is a subgroup, while the other cosets are not groups. They're just sets. This is because only H contains the identity element, and to be a group, you have to have an identity element. Let's call the number of cosets K. The number of cosets is called the index of H in G and is written like this. So we have D times K equals N, the order of G. In other words, D divides N. This means the order of H divides the order of G. This proves Lagrange's theorem. One last thing. Throughout the proof, we worked with left cosets, but you can repeat the proof using right cosets too. For abelian groups, the left cosets and right cosets are the same, but for non-abelian groups, this may not be the case. Either way, the proof is this. Pick a subgroup, keep making cosets until the group G is covered. Once you show that cosets don't overlap and are all the same size, you've proven Lagrange's theorem. Socratica partitions our videos into non-overlapping sets called playlists. Right now, you're in the subgroup of videos called Abstract Algebra, but we'll be adding many more playlists, very soon. Number theory, calculus, topology. If you don't want to miss our new cosets playlists, then please subscribe to our channel. And if you want to help us build playlists more quickly, please consider supporting us on Patreon. Thank you.